Please open in your learning workbook to page 159. Let's do another variation problem. When a constant force is applied to an object, the acceleration of the object varies inversely with its mass. When a certain constant force acts upon an object with a mass of 7 kilograms, the acceleration of the object is 4 meters per second squared. When the same force acts upon another object, its acceleration is 14 meters per second squared. What is the mass of this object? Okay, let's go ahead and solve this problem. Just like the previous problems, the first thing we need to do is identify what are the quantities that we can measure with numbers, and let's assign a variable to each one. So, force is something that we can assign a number to. And in this problem, force is constant. What that means for us is this is going to be our constant of proportionality k for this problem. Okay, next. The acceleration of the object varies inversely. All right, so the acceleration of the object, that's something that we can measure with numbers. It says acceleration, so we're going to use the letter A for acceleration. And it varies inversely with its mass. Mass is something that we can measure with numbers. For example, 7 kilograms. So we're going to use the letter M to represent the mass in this problem. Okay, so now that we have all of our letters, we can go ahead and write our variation equation. It says the acceleration varies inversely with the mass. So what's doing the varying? A, the acceleration. So we start with A equals a fraction with k in the numerator, and it says varies inversely, so down with the mass. Okay, so there we go. So this is our equation. A is equal to k divided by m. Now we're going to move on to the second sentence, and we're going to start replacing letters with numbers. When a certain force acts upon an object with a mass of 7 kilograms, all right, mass of 7 kilograms, so that's going to be m. The acceleration of the object is 4 meters per second squared. 4 meters per second squared, that's going to be A. Okay, let's put those values in our problem. A is 4, M is 7. And we're going to solve this for K. All right, so how do we solve this for K? K is being divided by 7. So if we want to get the K alone, what we have to do is multiply by 7, which is doing the opposite. All right, so 4 equals K over 7. We're going to multiply by 7 on both sides. Times 7 times 7. That gives us 28 equals K. So now we can put that in here to get our equation that allows us to predict the future. A equals 28 divided by m. Okay, so now we have an equation that tells us the relationship between acceleration and mass. If someone gives us an acceleration, we can find the mass. If someone gives us the mass, we can find the acceleration. By the way, this 28 is the constant force. Okay, so now our final sentence. When the same force acts upon another object, its acceleration is 14 meters per second squared. What is the mass of this object? So they're giving us a value of A. A is 14 meters per second squared. And so we're going to put that in our equation. So we get 14 equals 28 divided by m. Now this is a pretty easy equation to solve if you just take a moment and think. 28 divided by what number gives you 14? The answer has to be 2. So we're going to get m equals 2 kilograms. Now, if that wasn't obvious to you, you can still go through the algebra to solve for m. All right, let's clear the fractions. The first step would be to multiply both sides by m. So this and this cancel, and we get 14m equals 28. All right, 14m equals 28. Now divide by 14 on both sides. And we get m equals 2. So the mass of the object is 2 kilograms. Now, if you've ever taken a physics class, you would recognize that the situation being described in this problem comes from a rather famous physics equation, F equals ma. Force equals mass times acceleration. And if you solve that equation for A by dividing by m on both sides, you get that F over m equals A. It's the same equation we have here. The only difference is the F versus the K. But we know that in this problem, K represents a constant force, and that's why the equation looks slightly different. But this is a rather famous physics equation that we're working with.